Testing. Awesome. Okay, before we get started, I do want to here. Good. Yeah. Okay. So before we get started, I want to point out I posted an announcement about this, but one of the pieces of feedback I got whenever I put out the form to give feedback on how y'all were doing was one, that people wanted more practice problems, and then two, that sometimes the material was kind of hard to navigate. Like, what do I need to look at? What all goes with this chapter? So I revamped this chapter 6 and 7, where I started at the top with notes, so substitution and intro to elimination, and then whenever I put up your last little bit from chapter 7, it'll go right here below that. And then the practice problems and the answer key right below it, as well as the video key below it, and then the free response problems are also there. So I uploaded the free response questions. I actually uploaded them twice, so make sure that you have the most recent one, because I realized I put the wrong visual. So here's what the free response questions look like. There's drawing mechanisms and predicting products for substitution and elimination for chapter 6. And then after that, I put all my tutorials. So I have tutorials on here. And then I pulled the tutorials on the crash course because I thought that they were really good as well. So there's tons of tutorials on here if you need. I like my explanations because that's what you'll be tested on. And then I like having other explanations in case what I say doesn't make sense to y'all. The disadvantage of not having a TA, maybe we can mitigate some of that by doing your crash course things. And then any additional practice problems. So for this week, what I'm hoping we can do today is get to just the beginning of elimination reactions, and that's just what your test is going to be over, what we cover, or your quiz, sorry. Your quiz is going to be over what we cover up till the end of class today, and then we'll do recitation after that. And then tomorrow, I'm hoping to finish out the majority of chapter 7, and that's what you'll be tested over, but I won't have the opportunity to give you a lot of questions on that. So last year's chapter 6 and 7 recitation is a really good resource for you to practice, since we won't have our recitation in class that covers all of it together. So I really encourage you to practice that before the exam on whatever day that is. Okay, great. Any questions on the new updated way I organize things here? Yes, because I'm hoping we'll finish most of chapter 7 by tomorrow. If there's a little bit that we don't finish, I think there's like some stuff about hydrogenation and stuff at the end that we might not get to, but I think we'll cover most of it. But if there's some that we don't finish, you don't have to do the questions that relate to that. Okay. Any other questions before we get started? Downloading your notes, and I don't know. What about the quiz? The quiz is online, and it'll be opening. There it goes. The quiz is online, and it will be opened as soon as class ends today. It's going to cover up to what we've done today. So there will be there's a substitution reaction mechanism question, and like dissecting the anatomy of the reaction problem. And then there's a substitution, predict the products of the reaction. And then there's what's the last one? The last one is elimination. It's gonna have to do with sometimes eliminations can have one product and sometimes they can have 2 products, and we're going to talk about that today as well. And then there's actually 2 bonuses, just because I felt like asking you more questions, but they're a bonus. And then you get 30 minutes on the quiz since you have to do some file uploads. Okay, great. So all we have left to do with substitution reactions is solvent effects. And one big thing with substitution reactions or with what we're going to do today, is elimination reactions are very, very similar to substitution reactions. So I don't think it will be that hard for us to get through what we're covering in class today. So just to remind you, we did our deep dive on SN1 reactions, and we talked about how the nucleophile does not participate in the rate determining step. And then we also talked about the carbocation being formed, and that means that tertiary is more prone to react than secondary is more prone to react than primary in an SN1. So just to check, if you have a strong nucleophile, what reaction does that favor? SN2. And if you have a weak nucleophile, and if you have a primary substrate, and if you have a tertiary substrate, what if there's resonance? Carbocations are stabilized by resonance, so SN1. Okay. And that was where we finished off, is just the reactivity of carbocations, just to remind you. And we talked about benzylic and allylic carbocations stabilized by resonance. Okay, so the very last thing we're going to talk about is solvent effects. I think you need to worry about solvent effects least. Like, solvent effects are the absolute last thing I consider when I'm trying to tell if something is a substitution or elimination reaction, or if it's an SN1 or SN2. But it does have an impact on the nucleophilicity because of intermolecular forces, right? We need solvent because if we don't have solvent, our molecules can't interact. If you just had, like, imagine you have table salt and you're trying to react with someone else, there's something else, if you just put table salt in that other thing, there's no method for them to interact, right? But if you dissolve it in something, then those molecules are moving around in the water. So that's what we need to do also with reactions. So most chemical reactions, when you're upstairs in the lab, if you're doing research, there has to be some kind of solvent present to basically allow the electrons to interact with each other. That's the role that solvent serves. But that means that you're adding something else into the mixture of your two things reacting together. So you have to consider how what you're adding might impact the solvent. So there are kind of two solvents that we think about. There are nonpolar solvents and polar solvents. And then within the polar solvents, there's polar protic, which means there's a hydrogen available for hydrogen bonding, or aprotic, so there's no hydrogen available for hydrogen bonding. SN2 reactions generally are favored by polar aprotic solvents. The big reason for that is what kind of nucleophile is usually present in an SN2 reaction? Strong. So what does that usually mean? Why is it a strong nucleophile? Is it neutral or negative? Negative. So if you can imagine a negative oxygen, for example, and we put that down into water, what's going to happen with the OH minus as it interacts with the water? What kind of intermolecular forces? Hydrogen bonding, which is the strongest intermolecular force, which means your nucleophile is going to be spending a lot of time interacting with the solvent instead of interacting with anything else. So with strong nucleophiles, protic solvents really actually block them from being able to get to the goal of the substrate. So protic solvents are not good for SN2 reactions because they hinder. So aprotic solvents are better. There is still some polarity, which allows the solvent to dissolve. If there was no polarity at all, the solvent wouldn't be able to dissolve the nucleophile or the substrate, right? So you have to have some level of polarity. So since we have to have some polarity, we're choosing polar aprotic so that we don't upgrade to hydrogen bonds. The intermolecular forces will just be dipole-dipole, enough to dissolve the solvent or enough to dissolve the nucleophile and the substrate, and then not really have as many solvent effects. So we basically we have to balance between getting our stuff dissolved and be able to interact, but not having the solvent have too many negative effects on the reaction itself. So that's why we go with polar aprotic solvent for an SN2 reaction. For an SN1 reaction, you actually want the protic solvents. Can you think about why you might want a protic solvent for an SN1 reaction? The nucleophile is weak. A lot of times in SN1 reactions, actually, the nucleophile is the solvent. You've seen water as a nucleophile in an SN1 reaction. You've seen alcohol as a nucleophile in an SN1 reaction. So that's part of it, is the solvent can literally be the nucleophile as a product solvent. What else happens in an SN1 reaction that's kind of unique? The carbocation form. So the solvent, if it's more polar, will be more able to stabilize that carbocation. So we like polar product solvents for SN1 reactions. And a lot of times, like I said, those polar product solvents are literally just the nucleophile that's actually going to be interacting. So you don't have to add a third layer into that one. You can just have the nucleophile and the substrate, and then the nucleophile can literally act as a solvent as well. That's because it's weak, right? So it doesn't need to be dissolved in anything because it already will dissolve the other thing. When the solvent is the nucleophile, that's sometimes called solvolysis. So solvolysis is basically just another name for an SN1 reaction where the nucleophile is the solvent as well. Okay, so SN2 innate product solvents, because they have strong dipoles, but they don't have hydrogen bonding. So there are some examples that you might see. On your first response homework, I specifically noted, I didn't include solvent because I wanted you to focus just on the nucleophile and the substrate, but on your quiz and on future exams, there will be solvents as well. So usually the solvent is written around the arrow. Sometimes the reactant is written above the arrow as well. Sometimes the reactants are written just off to the side. But usually at least one of those things near the arrow would be a solvent. Polar aprotic solvents, they will solvate metal cations rather than nucleophilic anions. So they focus more on those carbocations as well. So they're not really bothering the nucleophilic anion, which is acting as our nucleophile. So if you compare the rate of the solvent between the two, like if you just have it in alcohol for this SN2 reaction, the rate is 1, and then it's up to what? Is that 10 million comparatively? So there's a significant improvement. If you're a graduate student and you use the wrong solvent, you're like, my reaction never worked, but actually it's just working really, 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 really slowly. So that's why you don't want to use a product solvent in your SN2 reaction. And this gives like a kind of a pretty picture, I think, of in product solvents, the nucleophilic anion is solvated or surrounded by the product solvent because of that strong hydrogen bonding, right? So you have this nucleophile and then these really partially positive hydrogens from their being bonded to something really polar. So this hydrogen bonding intermolecular force is so strong that the nucleophile is just surrounded by solvent and it literally just can't break free and get to the substrate that it's trying to get to. And that actually will impact the nucleophilicity, which we talked about very briefly yesterday, how you kind of tell what nucleophiles are stronger or weaker. And normally, something like fluorine would probably be a stronger nucleophile, but because it's in product solvent, it has the reverse of if it was in a product solvent. So just because the smaller, more concentrated that fluorine is, the more able it is to be able to attract molecules around it. It has basically a stronger negative charge, and so it can get more hindered by solvent. It's also smaller, so it's like not able to move through the solvent as easily because it's like so tiny, you know. But then it's opposite in aprotic solvents. So it's annoying that that's setting that off. Okay, so then in aprotic solvents, it's the opposite where fluorine would be the strongest because it's not solvated by anions. Instead, aprotic solvents tend to favor surrounding the positive cation. So like usually you wouldn't just have chlorine as your nucleophile, you'd have to dissolve NaCl, right, to get the Cl minus in there. And so if you dissolve NaCl in a highly polar solvent, the positive cation is going to be able to attract more of those dipole-dipole, and it won't interact as much with the anion. So it's just better to have a product solvent. So fluorine is smaller in size, so the charge per surface area is larger than an iodine. That's why it gets more solvated with product solvents, but that's why it's stronger in aprotic solvents. Okay, solvent plays an important role in SN1 reactions. Like I said, it's different from SN2 because usually they help stabilize that positive charge with their strong, I don't know why this is popping up in this weird way. But with their strong dipole moment, the super dipole as I call it, with a really strong negative, strong partial negative, partial positive, they're able to help that carbocation form. So they will use the strong negative to surround that carbocation and make it more likely and more willing to form, right? So forming a carbocation is pretty difficult because it's so reactive. That's not something that wants to happen. So if you put protic solvent, polar protic solvent, in your reaction mixture, that polar protic solvent can help the reaction happen. And if the polar protic solvent is also your nucleophile, then as that intermolecular force stabilizes the carbocation, the electrons can shift in and then form a full bond rather than just intermolecular forces. So it's almost like the intermolecular forces are the first step in the substitution reaction actually occurring, if that makes sense. The first step in the nucleophile bonding in. So when your solvent is also the nucleophile, it's stabilizing the carbocation, and then it very easily can shift into a full bond instead of just an intermolecular force. Does that make sense? Possibly? Maybe? Okay. Great. And this is just another picture of the same picture of the solvation happening as it stabilizes the carbocation. Okay, this is straight from the Solomon's book. I'm not going to read it all to you. It's a summary of what we just talked about. Halide nucleophilicity in aprotic solvent is the opposite of it in protic solvents. And then it talks about why some things have different polarizability, so that will impact, how they're going to be in different types of solvents. So I encourage you, if you're confused or having a hard time, to just read over this. I'm not reading it to you. It's basically just a summary, but I think reading this kind of like unlocked solvent effects in my mind. So, okay. And now I just want to kind of show you some SN2 reactions. This bromine is swapped out for the alcohol. This bromine is swapped out for the, this is called a methoxy alcohol that's deprotonated, is called a methoxy. This is protonated out for the sulfur group. Same thing here, and then cyanide. So this would be a good thing to practice for trying to get used to doing SN2 reactions, is you could just do that bromine with all those different things. And what kind of solvent would you use for this? Aprotic solvent, polar aprotic solvent, because you don't want the protons to be messing up the process of these nucleophiles. Okay, and then same thing here, you can use this to practice your substitution reactions. I'm not going to go through all of them right now. And then you can use this to practice trying to figure out what reagents you would need to get this product. So what nucleophile would you use to achieve this? Anyone want to take a guess? Ethanol would be weak or strong? Well, which one? Strong or weak? Dig in. Make a commitment. Is it negative or neutral? Ethanol. Ethanol is neutral, so that would make it weak. I think what you're thinking of is ethoxide. So ethoxide would be the negative version of ethanol, which that would be a very good reagent in this reaction. So that's ethoxide. And then DMSO. So you can work through those. And then there's even more review problems where you can practice the stereochemistry. So I want to leave these undone so that you can use them to practice. So they're all at the end of your PowerPoint. And normally we would do them like maybe as practice problems together in class, but because we're kind of low on time, since we slowed down yesterday, I just wanted you to see that they existed. Okay. Before we move on to elimination reactions, do you have any major questions on substitution reactions? Okay, our recitation today will be all about substitution and elimination, and you'll get to practice drawing mechanisms. It'll be so fun. So today we're just going to start on elimination reactions. We're going to dig deeper in tomorrow, and tomorrow we're also going to learn how to tell just based on the reactants and just based on the substrate and nucleophile if it's going to be an SN1, an SN2, or an E1 or an E2. But today we're just going to touch on eliminations. So substitution and elimination reactions are actually in competition, which is why sometimes we'll be given is because they're very similar. So sometimes we'll be given some reactants and it's hard to tell if it's substitution or elimination. I don't want you to worry about that yet. But I do think it's important to know that chemistry isn't like neat and clean. I think sometimes when we write things down on paper, we're like A plus B yields to C, and we get like 100% yield of C, and that's the only product we have. But in real life, if you mix A plus B, you usually get C plus D plus E, and then maybe it's interacting with a solvent too, so you might get like E, F, and G too. And a big job of someone who's actually an organic chemist is purifying all the different products you get to focus in on the main one that you want. And that's why you shouldn't do drugs from people on the street, because when they make meth, they're not organic chemists and they don't know that there are a lot of really dangerous side products, and they don't know how to clean or purify to just get pure meth. All they know how to do is mix things together and then sell it. So don't buy highly complex chemical compounds from people who don't have a degree in chemistry. Really a master's degree at the minimum in chemistry. That's why people who go into pharmaceuticals make so much money. Okay, so but chemistry is not just neat and clean. If you mix these two together, you'll get some substitution and you'll get some elimination. And so what we're going to work on later is predicting the major product. We won't predict, like, we won't say, oh, 100%. We'll say which one is major. And eventually we'll learn how to tell which one is major, which reaction is favored, but we're not going to do that today. So on your quiz, I will say substitution or elimination. You won't have to worry about figuring out what it is. You might have to figure out, will this be SN1 or SN2? And you should be able to do that based on knowing if it's a strong or weak nucleophile. Okay, or also primary, tertiary substrate. Secondaries can go either way. If it's secondary, I really rely on the nucleophile. So if you have a secondary, rely on the nucleophile. So today what we're going to cover is up through all about alkenes. We're going to do the overall reaction. We're going to go through it pretty quick because it is very similar to SN1 and SN2. Then we'll do the anatomy of the reaction, an overview of the two types of elimination, and then we'll talk about alkenes because elimination reactions make alkenes, and you need to know some about the stability of alkenes to be able to predict products of these reactions. So let's start with the overall reaction. When an elimination reaction occurs, actually both the proton and the leaving group leave. So this is the main difference between a substitution and elimination reaction. In a substitution, something new joins, and the leaving group leaves. In an elimination reaction, two things leave and a double bond takes their place. So two carbons lose something that was bonded to them, and then they just bond to each other instead, is basically what happens. So here's, and then an alkene is generated. And the anatomy of this reaction is really similar to a substitution reaction, which is why they compete. But we do still have the leaving group, which is also the electrophile or the substrate. And then we have a nucleophile, which actually in this case acts more like a base because it's stealing a proton, right? We talked about nucleophiles versus bases. Nucleophilicity is determined based on how much it acts in a substitution reaction. Basicity is determined more on how well it abstracts a proton. But we will still call it the nucleophile just for clarity's sake. So, but it is a nucleophile slash a base. It acts as a base because it steals a proton. And then you get the conjugate acid of that nucleophile as a product, plus an alkene and the leaving group. So here's the anatomy of that reaction. You need the good leaving group, just like you did in SN1 and SN2. Usually that means it's a polarized bond and it's stable after it leaves. And then you also need a good nucleophile. In this case, it acts as a base. So we have a nucleophile slash base, and we also want to make sure it's effectively able, so basic enough that it can steal a proton, in order for the electrons left behind to fill in where the leaving group leaves. So here's an overview of these reaction mechanisms. So in this case, ethanol is your nucleophile. Ethanol will steal this proton. It's acting as a base. It steals the proton. It leaves behind electrons. In an acid-base reaction, we only take the proton, we leave the electrons behind. Those electrons move over here to form a double bond. And as that's happening, the leaving group leaves. So just like an SN2 reaction, an E2 reaction happens all at once. It is a one-step concerted reaction. So that leaves us with the alkene. That was the electrons here filled in there. And then the leaving group left. So we have Br minus, and the ethanol is formed as the conjugate acid when the base stole the proton. Okay, I'm going to do a little bit on the visualizer, which I didn't turn on yet, so that you can see where these different electrons come from. Here's hoping the pins for my rocket book are working today, so that we can do different colored reactions. Okay, I want you to do this a little bit ahead of me. I'm not going to give you a ton of time because I really want you to have an hour to do recitation problems today, or as close to it as I can possibly get. But if we have, no, they're not. They've given up. So we have our leaving group is bromine. I'm going to draw the bond to the hydrogen as well, even though it's implied. And then I'll make my nucleophile. It's a strong nucleophile, so it's negative. So if you can, quickly draw the curved arrows. Give you like 30 seconds to draw the curved arrows. Okay. So the first thing is the nucleophile will steal that proton. And then the bond right here breaks because the electrons are left behind, and it fills in as a double bond here. And then the leaving group leaves. So I've drawn the curved arrows in the same color. It's struggling, man. I've drawn the curved arrows in the same color as the electrons where they started, right? So this nucleophile has formed a bond. The two electrons that gave it its negative charge has formed a bond with the hydrogen. And these two electrons that made up this bond, when the hydrogen departed, they filled in over here. And then the bromine left with the electrons that had been making up this bond. So now that bromine has a new lone pair and it's negative. Total, it has 8 lone pairs. Does that make sense? You see where all those electrons are moving? Great. Okay. So that's the overall mechanism of an SN2 reaction. This is, again, a bimolecular reaction. So what happens if we double the concentration of the nucleophile? You double the rate of the reaction. What happens if you double both the nucleophile and the substrate? You quadruple the rate of the reaction. So it's exactly the same as an SN2 reaction in that rate way, that both of the nucleophile and the substrate are involved in that rate determining step, right? So because both of them are involved in that rate determining step, the rate depends on both of them. So it's a bimolecular reaction that includes both the, in this case, alkyl halide and then the alkoxide. That's what we call it when an alcohol is deprotonated. Any alk you would replace with meth at prop. So it'd be methoxide, ethoxide, propoxide. So this one right here is ethoxide. So it's just deprotonated alcohol. Okay. This is another visualization of the E2 reaction mechanism for you. And sometimes we'll call the carbon that's like one away from the leaving group carbon a beta carbon. So the leaving group carbon is our carbon of interest. That's the alpha carbon. And any carbon that's one away is called a beta carbon. So the nucleophile removes a beta proton on the beta carbon. And that bond will break. A new bond begins to form here, the double bond, and then the leaving group leaves. Again, we have a transition state. This one's a little bit more complicated because one bond's forming here, one bond's breaking here, one bond's forming here, and another bond is breaking here. A little bit more complicated than your SN2 transition state. It has two other, there's not just an attack and a leaving. There's a something in the middle that happens, or two somethings in the middle kind of there. And then ultimately we get our alkene plus the alcohol that's formed, or the conjugate acid of whatever your nucleophile is, plus our leaving group is left. The energy diagram is actually exactly the same. Oh, yes.
Can you tell me what you mean by beta and alpha?
Yes, I can. I think it'll be easier explained on this. So it's used different, like there's a few different times you're going to hear alpha and beta carbon in organic chemistry. So I'll give you one example that's a little less relevant, and then I'll give you more. So there's going to be a lot of times in ochem 2 that you do reactions at this carbonyl carbon right here. So when that's the carbon of interest, that's called the alpha carbon. And these are called beta. And if you keep going, you do the Greek alphabet. So what is it? Alpha, beta, I think gamma is the next one. And then delta, but I don't remember the delta sign. And it goes in both directions. Both of these are beta, but there's only one gamma. So in our case, our carbon of interest is usually whichever one the leaving group is on. So that's alpha. And then we have beta carbons, and then we don't really care about the gamma delta carbons because in elimination reactions, the bond will be formed directly next to the leaving group, right? So we don't really care about that. It has to come from the beta carbon. And actually, because of that, there's sometimes two beta carbons, and there sometimes can be two different reactions or products that form in elimination. And we'll get to that in a little bit. But that's kind of what I mean by alpha and beta. So if you take a proton from the beta carbon, that's called a beta proton as well. You're welcome. Thanks for asking that question. So the energy diagram is pretty much exactly the same. Your transition state is at the top point, products, reactants, because it has that, it's all in one step. So there's only one high energy point that has to be overcome. I don't know why this doesn't say E1 mechanism. That's on me. I was the one who fixed that, and I fixed it wrong. Okay, so this is an E1 mechanism. E1 is a unimolecular reaction. So what does that mean? How many things are involved in the rate determining step? One thing. The first step of an E1 reaction is the same as the first step of an SN1 reaction. So where E2 and SN2 are similar, they don't compete as much. They do still compete, but E1 and SN1 compete hard. They're like, we'll say SN2 and E2 are like siblings where they like kind of compete. E1 and SN1 are like twins where they're like right next to each other and they're like really competing. Some twins, I don't know if they compete that hard, but that's like kind of how I imagine it. It's like these two kind of compete, these two really compete. One of the hardest things I think for students is kind of telling the difference between if it's going to go for an SN1 and an E1. And that's because there's so much gray area because you will likely get a high percentage of both of them because they're so in competition, because that first step is exactly the same. So our first step is the same. If our weak nucleophile acts as a base, we'll get the elimination product. If our nucleophile acts as a nucleophile and is trying to attack, then we'll get the SN1 product. So from here to here, you'll get a mixture of both of these. And actually, in this case, the elimination product is minor because they're competing so hard. Again, this should say E1 mechanism. So the leaving group leaves. This is slow. This is the rate determining step. You get your carbocation, exactly the same as our last one, as our SN1. If it undergoes an E1 mechanism, the beta hydrogen is abstracted. The double bond is formed to fill in that carbocation. And that happens much more quickly, and you get your E1 product. Alternatively, you can get your substitution reaction product. And remember, when you have a substitution reaction product, oftentimes there's that step 3 that doesn't get talked about very much that's also known as deprotonation. The deprotonation step. So these two are in major competition. E1 versus SN1 are going to be competing. It's just drawing that out for you again with the language behind it. So when it's aided by the polar protic solvent, right? So the water is surrounding the carbocation as it starts to form to stabilize the transition state as the chlorine leaves. And then you get a carbocation. In this case, it would be tertiary, so that's pretty stable. How could we make it even more stable? What's more stable than a tertiary carbocation? A carbocation that's stabilized by resonance. So like if you have secondary with resonance is better. If you have tertiary with resonance is better. So we can make this even better if we had resonance. In this case, we don't. So then this carbocation again is solvated by the surrounding water molecules, and then it's not too hard to see that that water molecule will come in and bind, or will come in and take the hydrogen and then form the double bond to fill in that positive charge. If it was an SN2 reaction, the water molecule would come in and bind here, or SN1, I mean, sorry. The water molecule would come in and bind here. So the free energy diagram for the E1 is very similar to the SN1, except it doesn't have that third deprotonation step, right? So there's only the carbocation forming, which is the rate determining step, and then the hydrogen at the beta carbon being abstracted to form your final alkene. So this is truly a two-step reaction. SN1 is like a two-step reaction. E1 is really just 2 steps. So that's step 1, and that pink is step 2. Okay, so let's talk about alkenes. We are right on track. I'm so happy. Okay, so we've talked about cis and trans alkenes, and I made you be able to identify it, but we didn't really talk a lot about the stability of cis and trans alkenes. So because of sterics, so the 3D shape of the molecule, the cis version of the molecule is less stable than the trans version of the molecule. So if the cis has so much steric hindrance around it that these electrons are repelling each other, and it's hard to be in that isomer. So the trans isomer is actually significantly more stable. One way that we can measure the stability of alkenes is through something called heat of hydrogenation. So how much energy would it take to go from this alkene to this alkane? And this is just an experimental measure. You don't need to like know these numbers or anything, but just to prove to you that someone has in fact, actually figured this out experimentally. There are heat of hydrogenations that have been calculated for all of these. The less stable, the higher heat of hydrogenation. That is something that questions get asked about. Which of these alkenes would have the highest heat of hydrogenation? Which of these alkenes would have the lowest heat of hydrogenation? Whenever I see that, I always write highest heat, least stable, least heat, most stable, so that I know exactly what I'm looking for and I don't have to remember the heat of hydrogenation anymore. So it's the kind of thing that when I got my exam, I would write that down on it right away so I don't forget it. I just do most heat, less stable. I could just do a little arrow. Arrow up heat, arrow down stable. So yes, these have been experimentally determined. So you can see actually unsubstituted unsubstituted alkenes are less stable, the least stable. Then if you have substituted but cis, it's a little bit less stable than that. And then substituted but trans is even the most stable. I think I might have said it wrong. Highest energy, medium energy, least energy. Least stable, medium stable, most stable. Did I say my words backwards? I think I might have. Sorry if I did. Okay. So we talked also briefly about how you could have just a plain alkene with 4 hydrogens around it. And then as you start swapping those out for R groups, what do we call that? Do you remember? Like if you have 1 R group or 2 R groups. We talked about it on cis and trans. It's mono-substituted, di-substituted, tri-substituted. I talked about that as you need a di-substituted alkene to be able to have cis and trans. So the more substituted something is, the more stable it is. Because it's donating extra electron density and stabilizing the double bond. So unsubstituted is the least stable alkene. Tetrasubstituted would be the most stable alkene. If you have something that's di-substituted, which one's going to be more stable, cis or trans? Trans, that's right. If you have something that's tri-substituted, you want the biggest groups on the opposite side. Same thing with tetrasubstituted. So if you have something tetrasubstituted and you have 2 really highly branched, like an isopropyl here and an isopropyl there, you want them trans, and then your smaller groups, also trans. But you want your biggest groups opposite. If it was biggest groups together, that would be less stable. So you're always going for the least sterically hindered. So when we have, this is just kind of letting you see, this is more stable than this because it's more substituted. Sometimes it's also called an internal alkene because it's like inside of it. But you can just know that it's more or less substituted. And then same thing here on this ring. This one has 1, 2 substitutions and then a third over here. So this is tri-substituted. This only has 2 substitutions. The other 2 are hydrogens. So this is di-substituted. So in elimination products, sometimes you'll have a symmetrical molecule and they'll be the same. So only one product is possible if there's symmetry. So there's symmetry here. You can cut right down the middle. Or in this one, all 3 of these are exactly the same. So any which way that it goes, again, symmetry. If you have 2 hydrogens present, symmetry. So no matter what, you're going to get the same product here and here. This is kind of I don't like that example. I'll talk about why this example is the way that it is later. But so you can see there's like primarily going to be 1 elimination product. There's only 1 elimination product. Why do you think it's at 79%? What's the other 21% if there's only 1 possible elimination product? Substitution, that's right. So if we put these together and you get an elimination, all of your elimination product is going to be the same, but there's also substitution products present. Sometimes the alpha and beta hydrogens are different. So you can get 2 different alkene products. And you'll get a chance to practice this on your recitation work today. But there's kind of rules about which one will be formed when. So on this one, if you have your base come on your alpha beta hydrogen, you'll get a more substituted, more stable internal alkene. If your B hydrogen from your beta carbon on this side is taken, you'll get a less substituted, less stable terminal alkene. Zaitsev's rule tells us that if we have a small, narrow nucleophile or base that's coming in to take our proton away, it will always give a higher percentage of the more stable alkene. So the way I remember that is Sitesef. It's sometimes spelled with Z and it's sometimes spelled with S. I don't remember which one's right. I think it's a German name, so people just change it to S because that's what Americans do. So Sitesef, smaller nucleophile, more stable. They all start with S or Z, but that's okay. So Sitesef, more substituted, more stable, smaller nucleophile. That's what we're gonna get. All those S's. Sitesef, smaller, stable, more substituted. Your nucleophile is smaller, you're going to get the Sitesef product, which is the more substituted, more stable. Okay. If you have a large, bulky base, so the quintessential version of this is tert-butyl groups. If you have tert-butoxide or if you have tert-butyl alcohol, this is a big, bulky group. Isopropyl also is pretty bulky, but not quite as bulky as tert-butyl. So you'll see tert-butyl a lot. And when you see tert-butyl, you should just like immediately think bulky. Tert-butyl is bulky. Tert-butyl is bulky. It has so many carbons and hydrogens around it. So Hoffman's rule doesn't have that nice thing where everything starts with the same letter. But Hoffman's rule is the opposite. It'll give you, it's a bigger nucleophile, a bulky nucleophile. It gives you the less substituted. It gives you the less stable alkene. So Sitesef, more substituted, more stable alkene. Hoffman, less substituted, less stable alkene. It's just the opposite. Sitesef, smaller nucleophile. Hoffman, bigger nucleophile. So you can see with this small ethoxide, that's just like narrow, a long chain that's more considered to be narrow, you'll get a higher percentage of the internal substituted. With the tert-butoxide, you'll get a much higher percentage of the external, less substituted. Can you think of why a big bulky one would rather give you an external, less substituted alkene? Why would it rather show a hydrogen on the outside instead of on the inside? It's harder to get to on the inside. What is that called? Steric hindrance. It's sterically hindered. This 3D arrangement of the molecule makes it to where it's hard for that nucleophile to come in and act as a base and take away a proton. So it's just, because it's so bulky, it's way more energetically favored that it's just going to grab the easiest one to get to. Okay, so this kind of just shows you Sitesef versus Hoffman. If you have a nice narrow product or nice narrow nucleophile, it'll favor the internal. If you have a big bulky one, it'll favor the external. Okay, that's where we're going to stop for today. We're going to do a deep dive tomorrow on, hang on just a second, on the stereochemistry of these reactions. There's also a weird thing that carbocations sometimes do in SN1 and E1 reactions that we need to talk about. And then we're going to talk about how you can tell the difference between substitution, SN1, SN2, E1, E2. You right now at this point should already be able to tell the difference between SN1 and SN2. So there will be a question where I'm going to ask you to tell the difference on your quiz. If you can't tell the difference, still give some kind of answer because you can get partial credit. What was your question? Yes, I can, and I'm not going to do it in my notes because I like handwriting better. So I'm going to draw the more and less substituted. You guys can do this with me as you want to. So the I always start with the basic alkene. All these are hydrogens, even though they look like fours. It's just ethene, right? Just the most basic alkene you can possibly have. But if we trade one of these out for an R group, I don't know why I put E just then. That becomes mono-substituted. If you trade two of them out for an R group, that's di-substituted. And you can have 3 different types of di-substituted bonds. You can have them where they're on the same, and remember that's not capable of cis-trans isomerism. You can have it where the substitutions are cis, or you can have it where the substitutions are trans. And then there's tri-substituted where you get 3 R groups, and tetra-substituted when you get 4 R groups. So when we talk about internal alkenes versus external alkenes, the way I figure out how substituted these are is I actually draw in my implied hydrogens. So this alkene has 1 implied hydrogen. Otherwise, this carbon has 1, 2, 3 bonds, so it doesn't need any more. 3 other bonds, so just 1. And then on this side, this carbon has 1, 2, 3, 4. So this is actually a tri-substituted. There's only 1 hydrogen that's left from your basic alkene. So this is a tri-substituted. And because it's kind of on the inside of this alkane chain, then we also call it internal, because it's on the inside. Now this one over here, this carbon only has 1, 2 bonds, so it must have 2 implied hydrogens. And then over here it has 1, 2, 3, 4, so it has no implied hydrogens. So this is di-substituted. So it's less substituted than the tri-substituted one by 1 hydrogen. And we call it external. We also sometimes call it terminal because it's on the edge or the, terminus of the carbon chain. Is this capable of cis-trans isomerism? Say it loud and proud. No, it's not capable of cis-trans isomerism. Great. Does that answer your question? Okay, so this one will be the more substituted. And how can we get a higher percentage of more substituted? What kind of nucleophile will we use? A smaller nucleophile. And to get this one, we'll use a big, bulky nucleophile. Okay, but sometimes, I don't know if I did a super good job of explaining it. If you have something like this with the bromine, if you take either hydrogen from either beta carbon, it'll give you the same product either way. So there's not 2 different products from this one because there's a plane of symmetry in the middle. So you can only get 2 different products if it's going to happen at an asymmetrical point. And the reason there was one that I didn't like on this slide is there are 2 possible products here, but it's very likely not going to give you. Oh no, there is only one. Oh, I thought the bromine was in the middle. Okay, because the bromine's on the end, there's only one. For some reason, I was thinking that was a secondary bromine and it could go either way. And it was telling you that the tert-butyl was bigger, but no, I was wrong. So that was my mistake. Okay, I can't believe it. We finished exactly when I wanted to. Has that ever happened? I don't think so. Okay, so we're gonna switch gears into recitation, but before I do that, I do want to answer any questions you have because you didn't get to do a lot of practice problems with me as we went. We're going to instead spend the whole hour of class of you doing practice problems for this. It's the second half of class. It's like your 2 recitations from this week are squeezed into one. Yes. No, the quiz stops at alkenes and trying to predict like, oh, there's 2 different products that can come from this. So I actually don't even think I make you predict 2 different products. I think I make you say which one can even have 2 different products on the quiz. So I was worried we wouldn't even get this far, basically. So, yeah, so up to today is where the quiz stops, and the quiz is opening immediately after class today. And it will be primarily substitution. There's 1 elimination question, and it focuses on the 2 different products being possible. And that's it. And then there's 2 bonus questions. And then everything we cover tomorrow, that will be on your exam. Whatever we cover through the end of class tomorrow, it'll be 2 hours of lecture, sadly. We're not going to do recitation tomorrow unless a miracle happens. We're going to finish out chapter 7. And then I've posted a good recitation for you to practice on your own to prepare you for the exam. It's a lot of SN1 versus SN2 questions. Okay, anything else on this chapter? Any other questions that we can do as a group? Do you feel like you are tracking with my lecture today? I feel like it's so similar to substitution reaction that it's not as hard. I think this is the hardest part, actually, the telling the 2 products. Okay, we'll take a class break until 12:05. I'm going to get your recitation packet because someone was in the eye tracker this morning and I wasn't allowed in my office. How exciting that someone decided to participate and earned money.